density of states rho of k and E of k. Before I continue with the discussion, let me briefly discuss the quiz that I had given yesterday, the quiz question. So, this was the quiz. The band structure of a particular semiconductor is given by, there is an expression given to you, and you were asked to draw the band structure qualitatively. So, that is the answer. There are two things to note. One is that the valence band is shifted, that is why it was k minus 5 whole square. So, the valence band is shifted here, and indeed this is nothing but an indirect band gap semiconductor. So, one of the objectives of giving the quiz was to how will you express the band structure mathematically for an indirect band gap semiconductor. So, what you will have is k minus the shift, whatever is the shift. So, at k is equal to 5, we have the minima, which is EC, energy equal to EC. The second thing that you note, which probably many of you have not noted, is the fact that the mass of electrons in the valence band, in the conduction band, and holes in the valence band were different. One was 0.2 m0 and the other one was 0.8 m0. That means 4 times heavier. The holes were 4 times heavier. The holes were 4 times heavier. What is the implication of that? The implication is that the band here increases much rapidly with energy axis here. You can see here, as energy increases, the band goes here rapidly in this direction, whereas this one tends to go much slowly. But actually, the energy here increases much slowly because m is in the denominator. If you see the expression again, let me keep the expression again, and you see here that m is in the denominator. When m is larger, the constant, which is h cross square by 2 mv here, is a smaller constant, and therefore it increases much slowly. In other words, they are not two inverted parabola of identical parabola, but they are different. The variation is different. This is because of different effective masses of electrons and holes. So, these are the 2 points to note in this quiz. Okay, we will continue with our discussion of the density of states. In the last lecture, we have seen that K, a state is characterized by K, which has 3 components, Kx, Ky and Kz. And by applying the stationary state boundary condition, we have seen that Kx, Ky, Kz are discretized. So, if you have a material of dimension Lx into Ly into Lz, then Kx is integral multiple of pi by Lx, Ky is equal to integral multiple of pi by Ly, and Kz can take values which are integral multiples of pi by Lz. The point to note is, just a second, I made a mistake here. I had used P, so P and Q, small p and q, where m, p and q are integers. So, the point to note is the values of kx, ky, kz are discretized, and therefore, k is discretized. The implication is that in the EK diagram that we have, the EK diagram, the values of k which we have here are discrete values, and corresponding to the discrete values we have discrete energy values. Corresponding to each k value we have discrete energy values. However, we have seen that the number of points here is very large. Each of these value varies from of the order of 1 million, and therefore, the number of points are very large. Essentially, this forms a continuum. So, that is why we normally draw EK diagram continuous, E versus K. The second thing that we have seen is, therefore, in the K space, this is the EK diagram, in the K space, or in the momentum space, we have the number of permitted points. So this is the K space, which means the axes are Kx, Ky and Kz. The number of points that we have are enormously large number of points here, and literally every point here represents an allowed K value. Every point represents an allowed K value. Our objective is to determine the density of states, which means the number of points between K and K plus dk per unit volume of the material. So how to determine that? So to determine this, first thing, we have applied stationary wave, standing wave boundary conditions, which means if I take a Kx value, a positive Kx here, the negative value Kx direction is automatically taken care. K in general represents the direction along which the electron is propagating. It is the propagation vector. Now, if I consider the positive direction, the negative direction is automatically taken care of because we had applied standing wave boundary conditions. Standing wave comprises of a wave which is moving in the forward direction and backward direction, resulting in the standing wave. Therefore, whenever I have taken a plus Kx, minus Kx has already been taken care. Therefore, we need to, when we count the number of points that to get the density of states, we need to take the positive values of Kx, Ky, Kz only. It means in the K space, which is a sphere, we need to consider only the positive octant. Positive octant. Please see, a sphere, you have hemisphere, and then 1/4 of that, that is the octant. Only the positive octant, which means you need to consider an octant which is like this. So octant is generally represented like this, the sphere, that is 1/8, the positive part of the sphere. So this is that portion of the sphere where you have only Kx positive, Ky and Kz positive, this portion of the sphere. I hope you can imagine it is the octant, 1/8 of the sphere. So you have half sphere, half hemisphere, which you divide into 4 quadrants, then you get 1 octant of the sphere. The octant will have positive Kx, positive Ky and positive Kz values. It is sufficient for us to consider only the positive K values, K components, because the negative K component is already taken into account when we wrote the standing wave boundary conditions. Now I want to count the number of points between K and K plus dk. Now, before I proceed to count the number of points, in the K space, what is the volume occupied by one point, or what is the volume occupied by one state? I should not say one point, one state. Please see that, let me draw a third diagram to make it more clear, because I will show here a little bit spread out the points, the permitted values. I want to draw the cube, just one second. So let me unit height, so what I have drawn is each point here corresponds to a permitted value of K. You see, what is this point? this point is 1, 0, 0. This point, that is kx, where m equal to, this is m, p, q. So m equal to 1. So this point is kx is pi by l, lx, pi by lx, and in this point ky and kz are 0. If you take this point, it is 0, 1, 0. And if you take this point, this is 1, 1, 0. And this point here is 1, 1, 1. So different values of MPQ will represent different points. You can take anywhere a cube in general. So if I take a k value here, then there is a small spread to this side. There can be a small, the next value. So let me show you first. What I have drawn is an infinitesimal volume in the K space. In the K space, a small volume, this is a K value. Just see the picture. If I change the Ky, this is Ky, this is Kx, and this is Kz. If I change Ky by this separation, which is pi divided by Ly, pi divided by Ly, then my k vector, the tip of the k vector can sit here. The tip of the k vector can sit at any corner here. The tip of the k vector, because k vector is defined by MPQ, values of MPQ. If you keep m constant, p constant and change q, then it will change by 1 unit in this direction. Do you follow? So different values of MPQ correspond to different points in the K space. One point here is shared by 8 different cubes. One point is shared by, this is one cube. For example, this cube, this point is shared by this cube. There is a cube on this side, there is a cube on this side, there is a cube on this side, and 4 cubes below. In other words, every point is shared by 4 cubes. Assuming that Lx is equal to Ly is equal to Lz, it is a cube. What is the volume of this cube here? The volume is pi by Lx into pi by Ly into pi by Lz, pi by Lz. So this is the volume of the cube. The volume, I will make a statement and then you see. The volume of one state, one allowed state, in the K space, the volume occupied by one allowed state in the K space is given by this, pi by Lx, pi by Ly into pi by Lz. Why one state? The state, there are 8 possible states here because there are 8 corners. However, every corner here, every point here is shared by 8 different cubes. In other words, it is just like when you consider the number of atoms in a cubic lattice, you have one atom shared by 8 cubes. Exactly like that. Here it is not atom, these are simply points. What are these points? These points represent allowed K values, which means if you connect here to the origin to any of the point, that will be an allowed K value, allowed state. And therefore, the volume occupied by one K state in the K space. So this is, we are discussing in the K space. In the K space is, so the statement is volume occupied by one statement, one state in the K space, is equal to pi by Lx into pi by Ly pi by Lz. In the K space, if I find out what is the volume between K and K plus dk, K and K plus dk, volume between K and K plus dk, K and K plus dk, I find the volume, and divided by volume occupied by one state will give me number of states between K and K plus dk. Volume in the K space between K and K plus dk divided by volume occupied by one state will give me the number of states between K and K plus dk. Per unit volume will give me density of states. So the volume between K and K plus dk, please see this, it means I am looking at a shell volume between this shell, two shells. So one is this shell, which is K. This shell means this shell, this point is lying on the first shell here, K, and the second one is between K and K plus dk. So this is dk. This is dk. So the second one here, that is this point, is lying on the second shell, and this is lying on the first shell. Please imagine a 3D, it's an octant. So one of them is one of the K is sitting on one shell, and K plus dk is sitting on the next shell. What is the volume between this? What is the volume between that? How do we get the volume? Volume between K and K plus dk. So this is equal to 4 pi K square into 4 pi r square is the sphere, surface area of the sphere, multiplied by the thickness gives you volume of the shell. So 4, but we are considering only one octant of the sphere, and therefore 1/8 into 4 pi K square dk. Volume between K and K plus dk of the shell of the positive octant of the sphere is 1/8 of this. This volume divided by the volume occupied by one state will give me the number of states. So the number of states between K and K plus dk is equal to 1/8 of into 4 pi K square dk divided by volume occupied by one state, that is pi by Lx into pi by Ly pi by Lz. This gives me number of states. We have to multiply this by a factor of 2 because we are considering momentum states of an electron. An electron can have two spin states which also contribute to the momentum states, and therefore we have to multiply by this factor 2 because here state refers to momentum states of electron. It is the K space, momentum space. So this is to account for spin of electrons. So this is the number of states between K and K plus dk. This per unit volume is the density of state. So density of states rho of K, density of states rho of K dk is equal to this divided by Lx, Ly, Lz, that is the volume. So you have 1/8 4 into 2, so that has already gone. So we have pi K square dk divided by, in the denominator there is pi cube, and in the numerator we have Lx, Ly, Lz here divided by volume, which is also Lx, Ly, Lz. Please see, this is volume occupied by one state in the K space. This Lx, Ly, Lz is the physical volume. Lx, Ly into Lz is the volume of the material. A material of dimension Lx, Ly, Lz, volume, the actual volume is this. This was volume in the K space. So this gives me the density of states. So what you have, what is left is simply this equal to K square by pi square into dk. I am sure many of you would have done this derivation earlier. Therefore, we have the density of states rho of k is equal to k square divided by pi square. Rho of k equal to k square divided by pi square. So just if you know the definition correctly, this is elementary algebra. We have calculated volume and density by elementary algebra. Provided you have the definition clear and the basic picture clear. So there is nothing to remember here in this derivation, just the definition has to be correct and simply follow the procedures. It's just 3-4 steps. Now, rho of k is the density of states in the K space, but normally we need the density in the energy space, because all the rest of the parameters which we get, like the probability of occupation, which is given by the Fermi function, that's also in the energy state. So we would like to have the density of states in the energy state, which means rho of E. How to get rho of E? We know this. We have already seen rho of E is equal to rho of k dk. The number of states between k and k plus dk is equal to number of states between E and E plus dE. This is what we have seen in the last class from the EK diagram. Therefore, rho of E is equal to rho of k. I can write this as dE by dk, which is equal to k square divided by pi square into dE by dk, 1 over dE by dk. We make use of the parabolic approximation. It's very simple algebra. As I have been saying, usually we consider the electron and hole states where the parabolic approximation is a very good approximation. So in the conduction band, we know the energy of electrons are given by EC plus h cross square k square divided by 2 mc. Therefore, E minus EC, or let me do dE by dk here. So dE by dk, dE by dk is, this is 0. So we have h cross square by 2 mc into 2k. And what is k from this expression? Because I want to eliminate k completely. From this expression, k is equal to E minus EC, here E minus EC into 2 mc by h cross square. This is k square to the power half. 2 mc by h cross square, this is k square. Therefore, k is equal to this to the power half into this to the power half. From the same expression, just rearranged, k is equal to this. So I want to substitute for this k here. So we have this. So let me substitute here. Therefore, this is equal to first k square by pi square divided by dE by dk. So that is just this. So h cross square in the denominator into 2k divided by twice mc. So 2 goes here, 1k goes here, 1k goes there. So we have mc by, is that all right? So I have simply substituted this k square by pi square divided by 2k into this. So this is equal to, we have k by pi square h cross square into mc I hope I have not made any mistake. And substitute for k from here. So we have rho of E is equal to, for k I will substitute this. So I have 1 over pi square, Okay, I want to do something here. Let me keep this 2 and 2, just because I want to take this together. Let me keep it as it is. So let me write this as 1 over 2 pi square. There is a 2 mc by h cross square, and there is a 2 mc by h cross square to the power half. So this is 2 mc by h cross square to the power 3 by 2 into E minus EC to the power half. The expression for density of states, in the conduction band. So normally this is designated as rho C of E is equal to 1 by 2 pi square into 2 mc by h cross square to the power 3 by 2 into E minus EC to the power half. What is this E here? Is the energy of electrons in the conduction band, which means if you look at the conduction band, so if you look at the conduction band here, where we had the EK diagram, you had the EK diagram like this. So this is EC, this is EV. We are looking at the density of states in the conduction band for E greater than EC. E is any value here in the conduction band, any value here, E in the conduction band. So E minus EC is this difference. Or if you compare this with your good old band diagram, then we are looking at the density of states available at an energy value E. So this is EC, the band edge, and we are looking at an energy value E in the conduction band. What is the density of state? So the density of state is given by this expression. It would be more useful to see what is the variation of density of states with energy E. But before that, if you follow exactly what we have done is to obtain the density of states in the conduction band. If you follow exactly a similar procedure, starting with, for the valence band, energy of holes in the valence band is EV minus h cross square k square divided by twice mv. Instead of using E is equal to EC plus h cross square k square by 2 mc, if you use this and find out the density of states for the valence band, you will get expression rho v of E is equal to 1 over 2 pi square into twice mv by h cross square to the power 3 by 2 into EV minus E to the power half. Please derive this. make a simple exercise and you obtain the expression here. Now here we are talking of energy of electrons in the valence band here. So E is less than EV. That is why it is for EV greater or E less than EV. This quantity is positive, otherwise it will become imaginary. So E is less than EV for the valence band. So this is for the valence band. These are the two expressions for the density of states. Now let me plot this. How would the density of states look like? So this is E. As I mentioned, we will always keep E on this axis. So we have all equivalent pictures, E here, and I want to plot rho of density of states, rho of E and rho of V. So this value here is EV, this value here is EC. How does it vary with energy? All of these are constants for the conduction band, only energy is the variable, so it varies as square root of E, which means with E this would vary like this. And similarly for the valence band, this would vary like this. Please see again, I have deliberately, this is going rapidly like this, here it is going, the slopes are different, because assuming that MV is different from MC, MV is much greater than MC. Sometimes you see in the books the density of states plotted like this, E here, and you have EV and EC like this. So it is square root of E variation. So this varies like this, and this one varies. So this is rho C of E, rho V of E, and this is rho C of E. So this is the density of states is now on this axis. But to keep a consistent picture, we will plot always the vertical axis will remain the density of state, the energy. So this variation is rho C of E, and this variation is rho V of E. The variation again depends on the effective mass. The density of states available depends on the effective mass of the carriers. Is this all right? So these are the expressions that we will need to calculate the carrier concentration, because as I had already pointed out, the density of states multiplied by the probability of occupation will give you the carrier density, and integrated over the band will give you carrier concentration. Before I proceed to determine the carrier concentration and discuss about the probability of occupation, I wish to draw your attention to a small effect which is right here. The major discussions we will do a little later, and that is related to the density of states in quantum well structures. I considered a cuboid of dimension Lx, Ly and Lz. This is Lz, this is Ly, and this dimension was Lx. A piece of semiconductor with the dimensions this. And correspondingly, in the K space, we got allowed values of Ky. So this is Kx, Ky and Kz. They are very closely separated points. So starts from about 1 million points within the first Brillouin zone. very large number of points. The separation between 2 points here, so let me just zoom it, and this is pi by Ly. Separation between 2 points here is this separation is pi by Lz, and separation between 2 points here is pi by Lx. Suppose I reduce this dimension. This was 1 millimeter, let us say 1 millimeter. I want to reduce this. As I reduce this dimension, that is, we are reducing the vertical dimension here, Lz. What will happen? Lz is reducing, which means the separation is increasing. I reduce it further, so the separation is increasing further and further. The maximum value here was pi by A, and A was approximately 5 angstrom. That is why, because Lz was 1 millimeter, I had 1 million points here. But if I reduce Lz, let us say Lz equal to 20 angstroms. I reduced one dimension to 20 angstrom, a thin sheet of semiconductor. What will happen? So the first point will be pi divided by 20 angstrom. This is Kx, Kz, the first point, Kz with Q equal to 1. So Kz with Q equal to 1, I have pi by Lz. The second point, Kz, Q equal to 2 times pi by 20, so 2 times pi by 20 angstrom, which is 2 by 10 angstrom, and Q equal to 3, that is 3 times pi by 20, and Q equal to 4 is 4 times pi by 20, which is pi by 5 angstrom, which is nothing but pi by A. The point is, when I have reduced this dimension to 20 angstrom, I have only 4 permitted values, 1, 2, 3, 4. The number of permitted values of Kz are just 4. From 1 million, it has come down to 4. You follow this? But Lx and Ly is the same, and therefore we have large number of points for Ly and Lx. But here it is completely discrete with just 4 allowed states. What is its implication? What will be the density of states? So I draw it again. In the K space, now I have first allowed point here and second allowed point here. Let us say this is for Kx for Q equal to 1 and Kz, Kz Q equal to 2. Whereas these ones can take, as before, very large number of points, very large number of values permitted for Kx and Ky, but Kz can take, for simplicity, let us say there are only 2 values it can take, because the thickness is very small. This thin sheet of a semiconductor turns out to be a quantum well. We will discuss this in detail, a topic which comes slightly later, but at this point you assume that it is a quantum well, but we will discuss about it. So this thin sheet corresponds to a quantum well, as we will see, but the important point to see is K values are highly discretized. What is its implication? K comprises of Kx, Ky and Kz. The first value of Kz should be at this height, Earlier we had sphere because a large number of kz values also. Now the first value of kz should be at this height, which means the k vector, the tip of the k vector must lie on a plane. Please see, if this is the axis, imagine on a plane where kx takes this value, first value, the plane here. Let me show this as a disk. So on this disk, k can take any number of values, any values, but the tip of this must lie on this disk. You see, this disk is perpendicular to the z axis, the perpendicular to the kz axis. It has to lie on that because the first value of kz will be that. But the other values, it can have any value of kx, ky, k, any value, but the tip must lie on this. Do you follow? Where will be the second value? When will be the q equal to 2? When it is q equal to 2, you will have a second disk. If you have not followed, just hold on, it will become clear. All k values must have non-zero kx, ky, kz. For propagation, unless you are propagating exactly in this plane, when kz is 0, even if it is you are propagating at any angle, the first thing is kz must have value equal to this, which means it should lie on the first plane. Where else it can lie? If k is sufficiently large, that means if energy is sufficiently high, remember that energy is h cross square k square by 2mc. So if k is very large, it means energy, the kinetic energy is large. So electrons with large kinetic energy can have a k here. The tip of the vector can sit either in the first plane or in the second plane, nowhere else. Unlike in the previous case, it was a sphere full of points anywhere you go. So that is why we had taken volume of the sphere to find out the number of points. But now we cannot do that because k can sit either the tip of the k vector, remember k is a propagation vector, can sit either in the first plane or in the second plane. How to calculate the density of states and what will be the density of states in a quantum well? We will discuss this in the next class. This is very important, and the density of states, let me tell you that you will see that the density of states will behave like step function. This is for the bulk semiconductor, and the density of states for a quantum well so in the k space, the allowed states will remain on disks for different discrete corresponding to different discrete values of q, and they are well separated now. Earlier q was also almost continuous, and therefore the k could have been sitting anywhere. If you see in one dimension, the k can have a value here, which means the tip of the k vector can sit anywhere here, like this. It could, or k can sit here, the tip can sit here, because there are no other intermediate values. So this is for q equal to 2, this is kz. And this is for q equal to 1. K cannot take any value intermediate. The states are discrete, and the consequence of this will be, we will see that the density of state will remain constant up to some value of energy. So below this there is no state, density of state, this is the density on this axis, remains, it is constant here up to, as you increase the energy here, the density of state is remaining constant. It starts from here, and please see the density of state here is constant in spite of the fact that you are increasing energy. When you reach an energy value here, this corresponds to Q equal to 1, and when you reach energy value corresponding to Q equal to 2, E corresponding to Q equal to 2, suddenly there will be a jump. Why there will be a jump? Because now the tip of the K vectors can sit on the second disk. So earlier it could have been sitting only on the first disk, but now it can also sit on the second disk. If the magnitude of, see this, if the length of the K vector is large, then if you take the K vector like this, it can easily sit on the second one. Length of the K vector is large means energy is large. E is equal to h cross square K square by 2mc, kinetic energy. So larger the value of K, it will get another disk to sit, which means the permitted states become large. Therefore, at larger energy values, the density of states is here. In fact, it is double. Earlier the density was here, here the density is double. But for all these energies, the density of states remain constant. And this has an implication in the device characteristics, as we will see later, that when we see semiconductor optical amplifiers, the amplifier bandwidth will remain flat if the density of states remain flat. So we will see these discussions in the next class.